Okay, you can still see my slides, right?
Yeah.
Yeah. Right. So thank you, everyone. Thank you, Guan, for the kind invitation. So today I want to talk to you about one of the most recent topics that I've been working on in the lab, and this is on how to automate Open RAN deployments, specifically for neutral host applications. During the talk, feel free to stop me at any time if you have any questions, or maybe if you're not that familiar with some of the concepts, I can maybe help and clarify them a little bit. So let's anyway start with an outline of the talk. So first of all, I wanted to talk to you about why we need a new architecture for cellular networks and how is this architecture being gradually deployed in 5G ecosystems, and that will be deployed even more in the next generations of networks. Then I will give some notions on the neutral host paradigm. So what is this neutral host deployments that we're targeting? And then on how to automate the deployments for the Open RAN, so the radio access network for next generation cellular networks. And then finally, I will talk to you to some use cases that are particularly close to me. One is Neutron, and the other one is an intent-based CI/CD and CT pipeline for the Open RAN. And we will see later on in the next few slides what all of these means. So first of all, so with the evolution of cellular networks, we are going toward a more and more flexible architecture that is able to be programmed via software. So we have 5G, for example, that is designed to support diverse use cases. So some of these use cases can be, for example, ultra low latency. So for example, imagine you have some autonomous car that needs to have a very low latency with the communication with other cars, for example, like to activate some critical systems like autonomous braking systems, for example, if there's an obstacle. We have a use case that is that of enhanced mobile broadband. So for example, if you want to stream videos at better quality, and maybe with virtual reality, augmented reality, and so on and so forth, you need you have different requirements. You don't have the low latency requirement anymore, but you're more interested in a high data rate, for example. And then we have IoT systems that maybe have even different requirements. They might need to stream some data at regular intervals of time, but maybe they're not that interested in having low latency or high throughput, but they just need to have, for example, a constant stream of data. And all of these different use cases bring up a need. That is the need to have a flexible architecture, so an architecture that can adapt to all of these use cases, and that it can also be programmed from a functionality standpoint to optimize, for example, the service provided to one of these use cases or one of the other use cases. So the bottom line is that we don't really have a one-size-fits-all solution, but we most likely need to adapt the network based on the current conditions of the network, but also based on the actual service that we want to provide to our different use cases that we have. So for example, we have that the network complexity is increasing. So we might have more devices. So in previous generations, we maybe only had handheld devices like cellular phones, but now we also have different devices that can be UAVs. So like, for example, aerial drones, or we can also have AR and VR devices like smart glasses or visors. So this goes beyond the cellular device to also different devices with different requirements and different characteristics. We also have increased complexity for the spectrum. So we have more spectrum to handle. An example of this is that of millimeter wave communication that wasn't there in previous generations, while now modern phones also have some millimeter wave antennas, and they can stream a huge amount of data in a matter of seconds, for example. And then we also have more complex protocol stacks overall. So the network is becoming more complex even from an architectural standpoint. And all of these brings up also another need, that is the need to have some automation. So you want to deploy network architecture to manage the network architecture in an automated way. And we will see in the next few slides what this means. But you also want to have some sort of intelligence that can understand what requirements you have in your network in that specific instant of time, and can work to adapt the network to better serve those requirements. We also have another characteristics of next generation deployments. So for example, we're going from a monolithic architecture of the cellular network that was, for example, in network generations before 5G, to a more disaggregated infrastructure where we have the network components that are split in different components. So we have network functions that before were carried out by a single box that was your base station. To now, these same network functions are divided into different components, like you see here. For example, you have an RU here. Let me maybe try to switch to a pointer so you can see that. Okay, you have an RU over here. You guys can see my pointer, right?
Yes.
Yeah. So you, for example, have an RU that carries out the RF component of the cellular protocol stack and the lower functionality of the physical layer, with functionalities that go from beamforming to precoding to inverse Fourier transform and so on and so forth. We have different components like the DU, that is distributed unit, or by the way, RU is the radio unit. So we have the distributed unit that carries out another portion of operations of the physical layer, but this time they're referred to as physical high. And these are, for example, the scrambling, the modulation, and so on and so forth, the MAC layer and the RLC. We have another component yet again, that is the centralized unit, both for what concerns user plane, so the data to send to the users and the users send back to the control plane, that carry out additional functionalities. So in the monolithic base stations that were typical of a traditional approach, you can see that we had a single box here that carried out all of these operations that I just mentioned. Well, now in this disaggregated solution, we have these operations that are distributed into different units. So for example, the radio unit, distributed unit, and centralized unit. And this is good both from a disaggregation component. So you have not anymore a single box that takes care of everything, but you have different components. And this is also good from a deployment perspective, because maybe you can manage multiple distributed units from a single centralized unit in a hierarchical manner. And then every distributed unit can have its own radio unit. So overall, you reduce the amount of units that are deployed to provide the same service in this hierarchical approach. We see another component here, which is very typical of ORAN. And this is like, for example, a near real-time RIC. RIC is the run intelligent controller. And this component can be used to control your base station. So all of these components that I just mentioned can be connected to the near real-time run intelligent controller, or the no real-time run intelligent controller. And these two can basically deploy intelligent applications and interface with the components that are forming your base station through some dedicated interfaces to act on some, to actuate some control. So for example, a use case would be this controller here gets the real-time data from the base station to figure out what's going on in the network at a specific time, and then run some intelligent algorithm that, for example, can be called XUp if deployed on the near real-time RIC, or RUp on the no real-time RIC. And then based on the current condition, these intelligent applications can send some control to improve the performance of the base station in real time, for example. And then this goes on and on in control loops. So there's a constant stream of data to the controller, and then potentially a constant stream of control actions to enforce in the base station. And one of these control actions, for example, can be to allocate more resources to one of the services that I was showing in the earlier slides, and maybe to resize the amount of resources allocated to different services that are not needing resources in that specific time. And this is just a very high-level overview, but just to give you some background on what kind of architecture we're moving toward, and what kind of architecture we're also considering in the remaining of this talk. Okay, hold on. Yeah. With this, we have our network components. So we have the RU, the DU, and the CU. They need to interface with one another, and they interface with some open interfaces. There you go. So for example, they interface both among one another, but also with the control plane that we saw, for example, in the rigs. We have open interfaces that are used to interconnect all of these components that potentially are produced by different manufacturers. So the idea is that you can have these different components developed by different vendors, and then each one of these components implements these open interfaces, and then you can use the interfaces to interconnect components even if produced by different vendors, which is very different from what happened in traditional networks where components were not really interoperable. So I could not buy a piece of equipment from one vendor, another piece of equipment from a different vendor, and make them work together. While in this paradigm, this is one of the interesting functionalities that is being proposed. And all of this, of course, is based on some concept, which is the concept of virtualization. So for example, you want to deploy all of these functionalities as virtual functions in your network. You have the disaggregation that I just talked about, and also the open interfaces that we're seeing over here. And then we have the programmable network nodes. So all of these nodes can be programmed in software. So for example, you can send some custom control, and then you can implement the control in software and enforce this control in real time. And then you can have the control loops that I was just talking about, for example, with the network controllers. Overall, all of these allows us to get to some architecture, which is this one in this picture, which is very complex. But the interesting thing that I'd like you to focus on are all this software on the margin of the picture. So in the middle, we see the network architecture. So for example, we have some LTE base station, we have some NR or 5G base stations, we have some other components. But the interesting thing is the ecosystem of all of this software that you see around that you can use to implement some functionality or the other of the cellular ecosystem. So for example, just to name a few, we have open interface and SRS run that you can deploy on generic purpose servers and use to actually start 3GPP compliant cellular stack. So you can get one of these two softwares, which are open source, by the way, instantiate them on your computer, and you can start a fully compliant cellular base station that is connected to a radio and can provide service to a cell phone that you can buy, for example, in any store. We have other software. So for example, we have some software provided by the Orange Alliance for the controllers. And then we have other softwares that span from service management and orchestration. So for example, ONAP, to some software for the core network. But the nice thing is that we have all this ecosystem of software that allows us to implement some functionalities that in earlier generation of networks, we couldn't really implement. And especially from a research standpoint, I would say we couldn't really experiment upon. While now we can start a base station, for example, and experiment by maybe devising some new functionality. So for example, a scheduler, implement it in a real stack that is compliant with what the base station actually runs, like what a real base station from an operator actually runs. And then we can demonstrate that solutions actually work, for example. So all of these very complex ecosystem allows us to go from some architecture that was in the traditional approach, where maybe the network operator wants to achieve some high-level objective. And the objective can be, for example, this one here in the box, like I want to stream some high-quality video to 100 users in a certain location. And the location here like is at Times Square, for example, in this specific period of time. So from 8 p.m. to 9 p.m. So in the traditional approach, when the operator wanted to achieve this intent, they actually had to send some engineering team, so actual people, like for example, to build some application implementing this intent here, and then to develop some control software that they can deploy on the base stations to achieve their actual objective. So all of this is great, but it requires some manual configuration for sure. So somebody needs to go there and configure all of these network base stations for this specific intent. And anyway, this will be a very ad hoc solution. So for example, tomorrow the operator wants to have a different intent, and we need to do this process all over again. This also brings us to high maintenance, because this solution cannot really scale, because you might have 100 intents and you might have 100 different things programmed in your network that you need to maintain. And then overall, it can also lead to poor performance, because this is based statically into the network and cannot really adapt, and it's not really flexible. And the idea is that with all these software and enhancements that I just mentioned, we can go from this traditional black box approach to something more data-driven and white box. So for example, the same intent, instead of having to be programmed by some engineering team, can be passed to some artificial intelligence or machine learning application. Like for example, the ones that we saw are running on the run intelligent controllers, like for example, XApps or RApps. And all of these applications can get the data in real time from the base stations, can parse this data and taking into consideration this intent here, and then can send out some control actions for the base stations to implement the actual intent that the operator wants to implement. So we don't really need manual operations, because all of this software is automatically generated and deployed. We don't need an engineering team that is there, takes the intent and converts that into actionable items that can be enforced on the base station, because we have some intent recognition. And the nice thing is that we can adapt continuously to the network conditions. So for example, this arrow here that goes into the AI/ML block is continuously streaming the current data condition of the network, so that the control actions can be tailored specifically for that instant of time where we have a specific condition of the network. So for example, we have, I don't know, 100 users, while a few hours later, we might have, for example, 1,000 users. And all of these can adapt in real time to the conditions. And then, given that we have this approach in place, we can also easily reconfigure the approach, just sending a different intent. So for example, this time I don't need to stream a 4K video, but maybe I need to have some very low latency application. And then I can just pass a different intent, and the network, the idea is that the network can self-adapt to this new intent that I'm sending out. So all of these can also be brought even a step forward by assuming that we don't really have every operator owning their own dedicated piece of equipment. So for example, every operator owns their own base station, every operator owns their own controllers. but we can have some shared piece of infrastructure, and we can also have some shared piece of spectrum and some shared piece of compute resources, where we can instantiate some network functions. So our base stations, our core network, our controllers, intelligence, and so on are not anymore a specialized piece of hardware that is tailored to carry out that specific functionality. So for example, the monolithic base station that I was talking to you earlier would be very specialized piece of equipment that can carry out the functionality of the base station only. But now we have all these functionalities that are embedded in some network functions that are flexible and can be instantiated through some software mechanisms on top of generic purpose servers. So we have some servers that are deployed and they are installed and they're ready to be used. So for example, when the operator comes in and tells me, I want to deploy this functionality. So for example, I want to deploy a base station to cover some specific area. The base station can be just instantiated on software on some server that is already deployed, but on standby and ready to receive some command. So the idea is that the network, base stations, core network, and so on and so forth, they become some flexible network functions. And then we have different operators or different tenants that can come in and say, hey, I need to use some portion of the infrastructure because I want to deploy a specific service. So for example, the G node B here. And while another tenant can come in and say, hey, I want to deploy a controller of the network, for example, or another base station, and so on and so forth. So we have all these tenants that are sharing infrastructure. So overall, we have fewer pieces of infrastructure compared to the case where each one owns their own infrastructure. But then at this point, we have the need to orchestrate our resources to take into account the requests and requirements of the different tenants, what they want to deploy on the shared infrastructure, and what resources do we have. So for example, in terms of spectrum and compute resources. So for example, the bandwidths that we can use, maybe if we allocate some bandwidth to the tenant one, we don't have the same bandwidth available to allocate to the other two tenants. Or if we have a pool of server and we allocate some to one tenant, then we need to remove them from the pool of servers that we can allocate to the other tenants. And all of these requires some orchestration and automation and intelligent allocation of functions like these ones based on the requests that the tenants submit. So maybe a request to cover a specific area. And also the availability of resources like in terms of compute servers or spectrum that we're allowed to use, and so on and so forth, on top of our shared infrastructure. And pretty much all of this brings us to our neutral host paradigm, where we have the shared infrastructure that not being owned anymore by each operator, is owned instead by a third-party entity, which we refer to as neutral host because it's neutral with respect to our operators. And we have our operators that instead of having to own and maintain all of their equipment, they just pay a fee, for example, to use some amount of resources, like, for example, to use some portion of the spectrum, to use some compute resources, or to cover a specific area, or to use some deployment sites. And they can submit some requests to the neutral host operator. And these requests, for example, can be, I want to instantiate some node base. So this is another way to call a base station to serve some specific area, like in this case, Boston downtown from 9 a.m. to 5 p.m. And this is ideally the way in which you can specify these requests. So for example, a very simple way in which the operator can say, I need this amount of spectrum, I need some server with this amount of CPUs, and I want to cover some specific area, right? Then we can additionally deploy some model. And these models will be deployed, for example, on the run intelligent controller in the form of XOps or ROPS. So for example, I want to deploy some models that controls one of my DUs. And this model takes to input the throughput and the latency of this specific DU, and then maybe wants to enforce some control that is related to these two metrics. So for example, you might want to serve some enhanced mobile broadband service, or some other service that requires a very low latency, and then they can deploy this model to send out some control action that can enforce this specific intent. Of course, this is not easy, let's say, because we have some challenges. And some challenges are, for example, just to optimize and manage the allocations from the multiple tenants that are sending different requests. These requests can also be in contrast with one another, for example. We need to effectively handle the sharing of our infrastructure from multiple tenants. So for example, isolating the service between the tenants. And then once we deploy a network service like a base station, we want to manage the life cycle of this base station and only keep the base station up when we need the base station. So when the operator needs the base station, and then bring that down after to save resources. But also if the base station breaks, we want to deploy another one, still in software with another network function. And then we want to control the behavior of the network through some intelligent applications like the ones I was talking about you earlier. So all of these, basically, in all of this, we need a way to automate deployments because it's just not feasible to program this manually at scale for a large number of base stations. So this brings me to the next portion of the presentation, which is how do we automate our deployments in OpenROW? So for example, in this case, this is a very active project that I'm working on, for example, as I was mentioning. We're using different tools. And don't worry if you're not familiar with all of them. And the idea is that what we want to achieve, we want to automate some functionalities. So for example, the deployment of network functions and reconfigurability. So for example, I deploy a base station and I want to be able to reconfigure the base station after I deployed it. We want to manage operations in a potentially dynamic wireless environment when the conditions of the channel are changing very frequently, potentially. We want to be able to share spectrum in between different technologies, like think about Wi-Fi and cellular. And then we want to manage AI and ML operations. So to do this, some of the tools that we're using are, for example, OpenShift or Kubernetes, that are some pieces of software to deploy the containerized applications and network functions on that I was talking about earlier, on generic purpose servers that are there, laying on standby and ready to be used when a request, for example, from an operator comes in. And then we use some other tool that is called Argo CD, and I have more on this in the next few slides, that allows us to synchronize the configurations of all of these services, network function and machines from some remote repository. So for example, you have some source of truth that can be on GitHub, for example, or on GitLab, and then using some approach that is called as GitOps, you can take some configurations from your source of truth and deploy them on the actual machines that are there and ready to be used by the operator. And some of these configurations can be, maybe you need some servers that are enabled to run low latency applications like the ones required for the base stations. We have another tool that is called Tecton that allows us to program some automated workflows. And these are, for example, step-by-step configurations that describe the steps to be performed on the network. So for example, when you want to deploy some application in a step-by-step manner, and I will show you an example of this later on. And then we have some other tools to build containers, because all of these is done through containers, either Docker, LXC, or other type of containers, so that we can deploy some network functions like the ones I was talking to you earlier on the underlying machines that are composing our testbed and, for example, running on with OpenShift or Kubernetes. So these are some of the softwares that we're using. And all of these, for example, is not just some abstract representation, but we actually implemented that using one of these tools that was the Red Hat OpenShift container platform. And here we see, for example, a picture of our rack of servers where we use some control nodes that are used to manage the operations of our cluster of servers. We have some worker nodes that, for example, are enabled for low latency operations, and we use them for the base station specifically. Then need, for example, very low latency connectivity with some radios that we have. While we use the control nodes to deploy some other services like the rigs, core networks, and intelligent applications. We use Tecton, that are the tools to write specialized workflows to actually instantiate the network functions that I was showing you. And then we use Argo CD, for example, to enforce some configurations, like these nodes need to have low latency capabilities. And then this syncs from a remote repository. All of these allows us to manage easily enough our configurations and our compute machines. So these guys over here. We can use some templates that we use as a start to make automated allocations through this tool here. And then we can instantiate some workloads in the form of containers or pods on some generic servers, like these ones here are very generic servers. They're not specialized to do any operation in particular. And then we can also add some additional requirements. Maybe these nodes here, they need to communicate with this software-defined radio rack that we have connected just to these servers over here. So all of these, for example, that might seem very complex and actually kind of is, we managed through these operations that I was mentioning you in the previous slides and all the tools that I just overviewed. Just to go some more into these kind of tools, we have like Argo CD, as I was mentioning, that allows us to get some configurations from a centralized repository. So for example, here you can see you can just sync the configurations, and these configurations are deployed automatically on the cluster machines. Or then we can have another tool like Tecton that implements the continuous integration and continuous deployment workflow. And all of these are, for example, workflows that we use and can be, and these workflows can be used to, for example, deploy a specific application, to build some specific containers, or to run some specific tasks. And all of these are, for example, a series of steps to be performed on the cluster machines, and that they start from some generic templates and can be used to deploy our base station, for example. And these generic templates look something like these simplified templates here, when we can specify different parameters, like the frequency of the base station, the USRP radio, so the actual radio transceiver that we want to use, the address of the rig, the core network, and so on and so forth. Some container that we want to start. So for example, here we want to start a command to start a base station, to use a specific image that is the container image for the base station that we have. Some environmental variables that we can pass, and then some additional resources. So as you can see, this is just a generic template, and we start, and then in real time, based on the request of the operator, we start filling in these fields. Like, for example, I want to use the image for the base station. I want to start this command. And then we use the tools that I showed you earlier to deploy our network. And an example of deployment can be this one, where we have different components. So, for example, you see the near real-time rig provided by the Orange software community. that runs different services as form of different containers. All of these containers implement this rig. Each one of them implements different functionalities. We have a core network that in our case is based on Open5GS, and we can have different, containers for all of the different services of the core network. But then we can have some base stations that are provided by an open source tool that we call OpenRunGym to deploy the base stations of the network. And all of this basically allows us to start a cellular network in a matter of tens of seconds, for example, which is really great if you think that the operator can come in with a request, and within 10 seconds, we can deploy and fulfill the request. That might be, I want to deploy a base station in this specific area, where before the request, there was only one generic purpose server. And then after we receive the request, we can deploy in a matter of tens of seconds. So all of this is the infrastructure that we're using. And now I'd like to proceed to the first use case, that is the one that we call Neutron. And this is an Open Run network loss architecture for zero touch run and spectrum sharing. When zero touch means that we can reconfigure the network without the need to go there and do things manually, but it can be done automatically. So for example, if you remember, we have the architecture from earlier. So we have shared infrastructure, some tenants that are deploying some network functions. And then we have a whole infrastructure that is the one that I just showed you that allows us to orchestrate and automate the deployment of these functions. So how did we realize all of this first use case for deploying these neutral host applications? So for example, we developed this framework that at a high level, we have some tenants here. So the ones that I was showing you in the earlier slide, that deploy some requests. So for example, the requests are the same that I was talking to you about earlier, like I want to cover a specific area. I want to have allocated some spectrum resources, and maybe I want to specify some policy. So what happens if my base station breaks? Do I want to bring it up? Do I want to just leave it there? And so on and so forth. All of these requests that are submitted by different tenants are collected by what we call a Neutron optimization engine app. So all of these collects our requests, and by running some optimization, crunches out based on the request and based on what we have at our disposal in infrastructure. So for example, number of servers, number of radios, compute resources, and so on and so forth, crunches out what we can actually instantiate of the network. So for example, I can instantiate, maybe I cannot instantiate all of 10 base stations that I was asked for, but I can instantiate maybe 8 or 9, covering some specific cell sites. And then once I have the allocations that I can actually fulfill, I send these allocations in step 3 to what we call Neutron Edge Data Center, which you can think about as the server diagram with the whole infrastructure picture that I was showing you in my previous slides. This one basically takes these allocations and computes some network functions to deploy. So this does the actual deployment of my base stations or node bases or MBs as microservices on my infrastructure to cover different cell sites, so different portions of the network. So one of them might be a downtown district, one of them might be a residential district, and so on and so forth. After this, that we deploy the service, we use the near real-time rig here to deploy some additional intelligent applications to fulfill maybe some objective of these tenants here. So maybe some tenant might want to optimize data rate and throughput for some of the use cases that I had at the beginning of the presentation, while some other tenants might want to have a very low latency of their communication between the users and the base station. So all of these basically runs the intelligence, both this one here and this one here, they run the intelligence to control the functionalities of my base station and the service provided to my users. And basically, they can be used also to manage the life cycle of the applications that I'm deploying. So for example, a base station breaks for some fault. What do I do? Do I bring it up again? Do I leave it down? Or maybe the requirements of the tenant change. Maybe they don't want to cover anymore a residential district, but they want to cover this time a downtown district. So I bring down the base station in the residential district, and they bring up the one in downtown, for example, and so on and so forth. Just by taking a closer look at one of these components at a high level, we saw that this neutron optimization engine RAP takes requests and crunches some policy. Basically, just to comment a bit more on this, the overall objective is to maximize the amount of requests that I can satisfy to maybe increase some gain for the neutral host that manages to have a larger portion of the infrastructure used by the operators. But we need to avoid conflicts between the different operators. So for example, we can deploy multiple operators, but on different portion of the spectrum. Otherwise, they would be conflicting. But also, we want to try and use contiguous portions of spectrum so that we can use a single base station to fulfill requests of different operators and maybe divide them in isolated slices or portion of the network. And then, of course, overall, we want to deploy our base stations, but we don't want to cause interference with other services and with the other operators. And these are some of the challenges that we have in this piece over here. Another very important component is the neutron data center that we saw gets the allocations from the previous component, and gets down the allocations from the RAP, and it can instantiate our network functions as these microservices, which, for example, can be a CU or a DU that serve different tenants. And all of these services are allocated different resources from a pool of resources that I have. So for example, I can allocate some resources to this network function, some resources to this, and some resources to this. But also spectrum, I can allocate some spectrum to each one of them from my available pool of spectrum. And then I can orchestrate managed intelligence that runs on the near real-time rig here as form of XApps. So for example, I can have some monitoring XApps that tells me what's going on in my network at every instant of time. And I can have some intelligence to enforce the goal of the operator, like I want to optimize the throughput or minimize the latency and so on and so forth. And then overall, once I know what I want to do, I need to actually do it. So I need to actually deploy all of these network functions with these characteristics and all of these intelligent applications on my actual infrastructure and connect to some radio units that are present on my cell site to actually provide connectivity. And once I do this, I have the service from the operator that is up and running. So the operator can start and serve their users. But my job is not done because I also want to continuously query the status of the service to make sure that the services are still up and running, and I can still provide a service to my operators. And maybe if some of these services breaks, I can promptly instantiate another one to replace it and keep providing service to the operators so that the operator can provide service to my users. And this is also can also be used, for example, to adjust my network allocations if necessary. So for example, the amount of CPUs to these servers, or the amount of spectrum, and so on and so on and so forth. Of course, in this, we have a ton of other services, which I won't spend a lot of time on. They're provided through Helm charts, which are another way to deploy autonomously and automatically on some Kubernetes-like clusters. And some of them are the RIC, some of them are the core network, some of them are some other databases, but I won't spend a lot of time on these services. After prototyping this, we have we tested the functionality of this. And how do we test that? So we tested this on the Arena testbed, which is a SDR-based testbed where you see the servers from before. And here you see we have rails of antennas that are deployed on the ceiling of our indoor laboratory, which is approximately, it's actually more than 2,000 square feet. And we divide this space in different cells. So these are the cell sites that I was mentioning. And these cells have a different coverage. So for example, we see different colors here, the coverage that we have. And we deploy some cell phones, like we have 4 cell site and 10 cell phones and 3 tenants or operators. And we use the infrastructure to fulfill the requests from my tenants that I was talking to you about earlier, which here are depicted in different colors. And this is our experimental setup. And then we measure some metrics. So for example, we see that to pull the image and instantiate the image, we actually take very few seconds. Actually, we are for pulling the image, so to get the image on the server, for example, we are below 1 second for all of them, but the ones for the rigs that are a little bit larger and they are pulled from a remote repository, while the other ones for the core network, X-apps and base station, we keep locally and are below actually around 0.1 seconds. So we for all these, we take basically below 1 second and below 0.1 second in most of the times. And then to actually instantiate the services, so from when the operator sends a request to when the services are actually sent, we take just approximately, I would say, around 10 seconds to instantiate a fully compliant cellular network where on our generic purpose server. So from the instant before, we have that we only have servers there that are not really doing anything. They're just staying there. And 10 seconds later, we have a fully compliant cellular network on these server machines. And this is actually great because traditionally to deploy one of these applications can take hours, I would say. And here we can do everything in around 10 seconds, pretty much. So this is on the instantiation time. That is great, but let's see some of the performance that we have. And here we have that we consider different use cases. So we consider the first use case is that uses baseline. So this is the no sharing use case, very traditional approach. Every tenant or every operator owns their own cell site. They don't share anything. They have 30 megahertz of spectrum, and then they serve users just like that. Then we have a different use case, and the use case is where the operators are sharing and they still have the same 30 megahertz spectrum. So we have Neutron that controls the 30 megahertz overall of spectrum that we have, and can allocate the cell sites on the infrastructure that I showed you. I can allocate requests from different tenants, sharing this bandwidth and sharing the infrastructure from before. In this case, we have that each of the cells that we deploy can provide connectivity over a 10 megahertz block inside this 30 megahertz spectrum block. Then finally, we wanted to bring things a bit forward, where we share the infrastructure as in the previous case, but in this case, we don't have 10 megahertz, but we have only 10. So we reduce the available spectrum that we have. Sorry. And all of this is represented in the picture here. And we have, for example, the no sharing case that is in blue, the sharing with 30 megahertz of spectrum in orange. And in yellow, we have the sharing with 10 megahertz of spectrum. And what we see, what we can appreciate, is that basically when we share the infrastructure among the different tenants, since we introduce some sort of coordination between the tenants, but this is a sort of coordination that the tenants don't really need to care about, but this is managed by the Neutron framework. and is transparent for the tenants. We have our throughput basically increases when we share our infrastructure. So this would be the orange piece here, when compared to when each tenant owns their own infrastructure and doesn't share anything. So the blue portion here. And this is also true in the when we share the infrastructure with lower amount of spectrum, so like the 10 megahertz. Of course, this performs slightly worse than the first sharing case, but still performs better, or let's say comparable to when we have the no sharing case. So this would be a gain from the baseline that we consider, and this happens both from a total run point of view, but also from an average service provided to each of our 10 users in this case. Another result here, we see some different metrics. So for example, we see the cumulative distribution function of the UE throughput, so the throughput of every user, the modulation encoding scheme that we have in downlink, so the higher the better, and then the uplink SNR that we observe in our network. So as I mentioned before, we have that both our sharing scenarios outperform the case where we're not sharing anything. And we have the additional thing here that when we share the 10 megahertz spectrum, we already have an improvement in throughput and MCS, so in modulation encoding scheme, we compare to the not sharing scenario. But in this case, however, we're using a lower amount of spectrum, so meaning that we're only using 10 megahertz of spectrum instead of 30, and the remaining 20 maybe can be allocated to something else, so to some other application. And we can see this here. However, there's obviously a catch, and the catch in this case is then when we have the lower spectrum use, so the yellow line here, when we share 10 megahertz of spectrum, we observe more interference than when using the 30 megahertz of spectrum. This is sort of expected, and depending on the use cases that the operator is targeting, this might be acceptable, or the operator might opt to use a larger amount of spectrum. So for example, the 30 megahertz of spectrum compared to the 10 megahertz of spectrum. And this was my first use case. So before I move to the second use case, maybe you guys have any questions for this?
What do you question to the end? Thank you.
Oh, okay. So the second use case that I want to talk to you about is that. Oh, you have a question there?
Oh yeah, you can ask me.
Oh, sorry. Yeah.
Okay, so go back to the previous slide.
Oh yeah. This one.
One more previous, please.
This one.
Yeah. So when you mentioned sharing of spectrum in between the UEs, so why are you taking like the average UE through? Wouldn't it be like different for different UEs, and then because of the different spectrum sharing of different UE, or is this just for one cell that you use?
Yeah. So thanks for the question. So just to clarify, well, this is the total run throughput, so the overall that we have in the network. While this is we take the results of every UE and we make an average. So the point that we want to be sure, so it's certainly true that we might have different UEs that are allocated different portions, but what we wanna observe is that we don't only improve things from a overall point of view, where it might happen that maybe certain users are actually performing really well while other users have really worse performance. but we want to take this average to make sure that also every UE on average receives better service, and not only maybe we have some UEs that are receiving a very good service, other UEs that are receiving a poor service. And here we also have the crunch numbers, where you can also see the median that we have here, and per UE alongside the average per UE. I don't know if this answered the question.
Yes.
Yeah, thanks.
Thank you for the
Yeah.
My question is, besides submitting requests regarding network requirements, can the tenants also submit or deploy their own X apps, for example? You think that's going to be
What was the second part? So besides specifying what to deploy?
Yeah, besides the network requirements, like the spectrum and the keyboard and everything, can they also deploy their own X app?
Yeah.
Like, do you think? Yeah.
Yeah, that's the overall idea. So the operators, for example, let me go through one of the previous slides, which is probably here. So we can specify some model that we translated, for example, as an X app that they want to run and use to control some base stations. So they would deploy the X app through some directive like this. And this could be, for example, an X app from their own catalog, besides one of the available ones on the neutral host, because every operator might have their own, for example.
Thank you.
Yeah.
You have one more question? Okay, that's the question. Okay. Before we continue. Okay.
Could you go to the slide 14?
14 is this one, right?
Yeah. So one of my question you already answered when you talked about Helm charts. That was about how complex configurations are being handled.
Mm-hmm.
But when it comes to the Kubernetes infrastructure, are you using any proxies or service discovery applications like CNCF tools to, let's say, check and yeah?
Yeah, thanks for the question. So not as of now. So basically, well, this is implemented in OpenShift, which is kind of similar on Kubernetes with some additional improvements. But the short answer is that in this specific work, we're not doing service discovery, but we're working on service discovery for some extension of this work, where we might have some services that are advertised to the network nodes through tools such as Apache Kafka, for example.
Thank you.
Yeah.
We can leave the chance to the end. Okay, great. Thank you. Then
Okay.
Go ahead, please.
Yeah, so I was here, which brings me to my second use case, which is that of an intent-based CI/CD and CT pipeline for the Open Run, where CI is continuous integration, CD is continuous deployment or continuous delivery, depending on who you ask to, and we're introducing the concept of CT, which is continuous testing. So basically, we want to continuously deploy applications. So for example, from some remote repository, and we're using the Open Interface repository as an example of this very early stage prototype. And what we want to do, we want to deploy the latest version of the software. This is an open source software that implements functionalities of cellular base stations and users. And we want to perform some continuous testing of this functionality. So for example, the idea is that we have the team working on this that periodically, like every week, releases a new tag of their software. And when there is a new tag, we want to pull the latest version of the code, build it in a form of a Docker container, save the container on our registry, deploy the container on the infrastructure that I showed you, and then run some automated testing over the air. This is done, for example, like through some Tecton pipelines that I was mentioning. So a pipeline to do that. And this is an example of a pipeline that is running and that is testing the functionality of this software. So the question is, we're not really the developers of this. So besides the fact that it's really cool to do, why do we want to do this? So where do we want to test the functionalities of some software like this? And this, by the way, started with Open Interface as an example, but we're expanding through other Open Run softwares like, for example, RIC, XApps, interfaces, and so on and so forth will be also considered in the future. So for now, the nice part is that, let's say we have some functionality that is being developed, and we want to test this functionality, but we don't really want to do them manually because doing things manually is not really reliable, and and very time consuming. We want to do that automatically and in a way that is reproducible and reliable. So basically, we want to continuously test, for example, some functionality that is developed, like imagine a new scheduler for cellular applications. So what we do, we take this functionality and we package through a patch that can be applied to our software, like to Open Interface. After this, which is the only manual step involved, we have our pipeline that is automatically getting the latest version of the Open Interface base station, in this case, applying our patch. So for example, implementing our patch on the base station to implement our new scheduler. Then this automatic pipeline builds automatically the container that can be a Docker container, for example, or an LXC container, and then performs some form of automatic over-the-air testbed on the Arena testbed that I was talking to you in the previous slide. So for example, pieces of this test can be deploying automatically the base station, as I was showing you in the previous slides, and then interfacing this base station with some UEs that we have deployed in the lab. And these are 5G modems that are Sierra wireless modems that are basically like your cell phone, the chipset in your cell phone, but they're a bit more convenient in the sense that you can connect them and control them from a computer. You can implement some automatic testing here, like for example, to test how well the base station can serve the users with the new functionality applied. And this is done over the air, but we can also do similar things on Colosseum, and this is actually a thing that I'm working these days to replicate this automatic testing on Colosseum that uses different kind of containers, different kind of automation, and so on and so forth, and different kind of radios also, by the way. After this, we run automated tests with either one of these procedures. Now we can collect some results, build a history of results so that we can compare more recent tests with the history that we have. And for instance, know at a glance if a certain test was successful or if a certain test failed. In which case we might need to go back and repeat our procedures. So maybe there are some bugs. It often happens. We patch the bugs and then we go on and automatically test again. Or maybe a new version of the code is released and our patch needs to be applied in a slightly different way. And we need to modify that to comply with the latest versions of the code. We've been running this procedure since July, actually. So I don't have the most recent results, but we've been running these procedures for 3.5 months automatically every 6 hours in the lab. And testing different configurations. So for example, here we have our different configurations. We're using Hyper for this, different data rate targeted, so 10 megabit per second, 20 or 30 megabit per second. In this case, we have one base station transmitting to one user. We have the achieved throughput from each test, and here we have on the x-axis the day and time actually where the test was actually run. So for example, this goes from July 4th to pretty much should be a snapshot of a week or so. Basically, what we can see at a glance is that, for example, some configurations are really good, like 10 megabit per second is good, 20 megabit per second is also good, but then we have some issues here, and we can see at a glance that we have some underperforming results for the 30 megabit per second configuration. And here we can go and investigate, for example, why did this happen? Was this a fault of the functionality that maybe couldn't sustain the higher data rate? Was it an issue of the protocol stack that maybe had some issues and we had underperforming points? So we see, for example, that we have these underperforming points, and we can generate automatic tickets for the developers to actually look into them and try to improve things. Another view, for example, of this continuous integration and testing dashboard is that we can also build this history of results that we compare against, like in a statistical manner and not only as a looking at the overall performance dashboard. And we can have, for example, the collecting metrics. So each one of these lines is a test that was performed. We can collect per date, and we can collect different configuration, like we're on UDP with 3 different configurations that we have. And we can use this dashboard to collect this history of results and build a history and compare the new tests with this. Finally, I mentioned that I'm transitioning this to the Colosseum ecosystem, and this is just kind of a video that show you how the various tasks are performed. So there are very many tasks performed. Everything is performed automatically through Ansible. So we're building an LXD actually container through Ansible. That are the containers running on Colosseum. But then what we will do, and actually this was completed in the last few days, we have an automatic testing jobs for Colosseum, and then we're working on the actually data collection and maybe public visualization of results on the Colosseum testbed in a similar way to what I was showing you earlier. So this is just shown at 8 times the speed. So this will just go there. And this was actually the last slide for my presentation. So if you guys have any questions, I would be happy to take them.
Thank you very much, Leonard. So,
Yep.
any more questions?
So one question from my side. So as you told here that you also have Linux container, Docker container, and if there any issue, you can create a ticket. So I was wondering how your tracing and logging is happening all through these components. What kind of tool you are using to troubleshoot the issues when they are happening?
So are you talking about tools like to fix the issue, or are you talking about tools to collect the results and generate reports? Which can you elaborate a bit more on the question?
The later one, collecting the records and metrics and everything, and which, all the distributed components metric and displaying it at one place so that we can fix the issues which are happening.
So for example, to build something like this or something like this, right?
Yeah.
Yeah. So basically, there's this task that for now is iPerf that goes from the base station to the user. And what happens is that this task generates some reports on the performance of iPerf. And then they are streamed to some containers on the OpenShift testbed that are there and dedicated for the analysis of these results. So the way it works is that the test is performed, the user then generates a report and then sends the report to some container, some Flask APIs that the container implements. And when the container receives a call to these APIs, basically receives as a payload a summary of the iPerf report that the user generates with, like, I don't know, for example, throughput for every second, or CPU utilization, or all of these metrics basically are on the reports. And then we have some Python scripts that parse the results and put them nicely in some CSV file that are then queried either to generate a table like this, and this is just a web page implementing some HTTP tables, or a plot like this, which is a plot generated by JavaScript. After this, the idea is that you can see that there are some underperforming kind of points, and here you can check when the test was run. For example, here we have the test run around January 8th. No, actually, sorry, July 7th here for this point here. This is July 6th. And you can go there and check which version of the open interface software was run in that specific moment. And then you can just go there and do the debugging. We don't really have an automation for that as of now, as we're focusing on the testing. But I believe each software that you're testing might have different tools to troubleshoot errors and perform some performance testing.
Yeah, thank you.
Yeah.
Any other questions?
Maybe. Let me see if I can forward this kind of to the end, because this takes a long time to build, and then other tasks are just export the container, and then basically there's a summary of the various steps along it took and stuff like that. These are mostly for debugging issues, but wanted to show you some operations going on, and not only from a high-level perspective.
Yes. So you mentioned about using AI ML based XApps that would be deployed in the SPED. So what are like the general scenarios that you use for, like what measurements do you see, and then what parameters are you controlling? So just
Right.
about it.
So what we've been focusing until now is, for example, to control very specific parameters. So the scheduling of each slices of my network, and the resources allocated to each slice of my network. So for example, you can give more resources to an MBB slice, fewer resources to an MTC or URLC slice. And the parameters we've been streaming from the base station to the XApp are, for example, the throughput, are the amount of resources requested to the user, and the ones that are actually allocated, to understand if you are allocating enough resources to the users or not. The occupancy of the buffers of data to be sent to the base station, and the amount of packets. But this is just what we are doing in this specific scenario, but then this can be expanded to also include different metrics on the XApps. Don't know if this answered the question.
Okay. Yeah, last question. We're running out of time.
Yeah, it's a little bit off topic, but you just mentioned that you can like use two slices, one for MBB, the other for MTC. Is there like an open source software that can emulate MTC usage right now, or
Yeah.
regular?
Yeah, actually, let me see if I have a link in the previous slides. So that would be, I don't have a link. Maybe that would be through the OpenRun Gym software, which wait, something. Can you guys still see my slides, or did they go away?
Yeah, we can see.
Okay, so here in the bottom, there's this openrungym.com website, where we are releasing the software. We're publishing the software that we're releasing open source, and some of it, like for example, is a base station tool that is called Scope, and you can use to run some functionalities that we implemented on top of SRS run, actually, or as it was the time, SRS LT, and you can use it to implement slicing or scheduling of different algorithms. We're currently expanding this to open interface, but we don't have a stable release yet. But when we will have, we will be published on the same website, basically.
My question is like, do you have like something to use for NPC, like NB, northbound IoT users. So
Oh.
there are some differences.
Oh, sorry. Yeah, no, the way we've been doing that, we divide the slices and then we send a different traffic to different users based on which traffic they belong to. So for example, we take the traffic stand from the 3GPP definitions for each of these slices. And if the user is EMBB type, we send a EMBB type of traffic. Or if the user is URLC, we send a traffic distributed as a URLC slice. And for this, we're using a tool that is called TGen, which is the Colossian traffic generator, where we have traffic scenarios available, or another tool is MGen. But the traffic specifics are taken from the 3GPP specifications, for example. We didn't implement the traffic generator ourselves. We just used what was there on Colosseum with the definitions from 3GPP.
Okay, thank you, Leonardo. So we are running out of time. So let's thank Leonardo very much again.
Yeah, of course.
Okay, thank you, Leonardo. So we hope to invite you again next year.
Yeah, of course.
And you are very welcome to visit Buffalo at your convenience.
Yeah.
And hello to everybody in the lab. Thank you very much.
All right. Thank you. It was a pleasure.
Hello to Professor Malodia.
Yeah, of course. Thank you. Bye,
Thank you.
Bye, everyone. Bye, bye. Thank you.